Um, Good evening, everyone. This is the NPTEL problem solving session for the course Introduction to Robotics, and this is the session for week 11. In this week, you have studied about mostly about the CS aspects of robotics. Okay, like how do you define the probability distributions of different, you know, kind of states that are used. Okay, and like basically how you express the quantities that are relevant to your robot, like the position, orientation, velocity, etc., of your robot in a probabilistic manner. Okay, so that it is applicable in a more stochastic setting, because in real world, we cannot do deterministic, right? Because deterministic is just an approximation. Okay, because see, uh, I will tell this first, like the very word model, right? It means that you are making assumptions. Okay. So when you say that you are making a model of a physical phenomena, that means that you are making some assumptions related to that phenomena. Okay. And using those assumptions, you're trying to write the behavior, expected behavior using the model. Okay. But in reality, you know, the your actual behavior, okay, it will not be the same as your, you know, will not be the same as your model's behavior. Okay. Why it will not be the same? Because you have made some assumptions. Okay, you have simplified the problem. Okay. And by the fact that you've simplified the problem, you have changed the model. Okay, you have changed the system slightly. Okay. So like this is the reason why the actual behavior will never be same as your what the model that you make. Okay, model can be like anything, like your kinematic, you make kinematic model or you make dynamic models. Okay, so essentially if we talk about the physical things, or let's say your robotic arm, okay, so there can be a kinematic model. Okay, so what does kinematic tell you? It tells you the geometrical relationships. Okay, and then there can be dynamic model. Okay, they tell you relationship between the geometry and forces, right? So see, if I, for example, you know when we were doing the robot arm, right, we assumed, okay, that all links are rigid. Okay, but in reality nothing is perfectly rigid. Okay, any material, no matter how stiff it is, or how much force you have to apply to deform it, every material deforms. There is not a single material in this whole universe that does not deform, or basically that does not have a relative displacement between its particles, component particles. Okay, what does rigid actually mean? Let us say that this is your body, let us call this B. Okay, then if I assume that this body is made up of some particles. Okay, okay, so if I assume that this body is made up of some particles, then the relative distance between any of the two particles, it remains the same irrespective of the force applied on the body. Okay, that is what we mean by a body to be rigid. Okay, let us say this is delta. Okay, that delta is your distance between any two arbitrary points. Distance between, let us say we call it P1 and P2, P1 and P2 for all P1, P2 in B. Okay, so it's not like you can say this, like for a section this is true, and then for some other section this is not true. For the whole body to be rigid, for each and every point belonging to the body, okay, the distance between any 2 points, okay, this delta must be constant, right? This must not change. This is what we mean, when we say that a body is rigid. But again, in reality, delta is never a constant. Okay, it is never a constant in reality or in physical systems. Okay, so how do you model this now? Okay, because see, you had made your model earlier assuming that it was rigid. Okay, but now you want to change your model because you know that the model is not complete. Okay, so how do you change your model to incorporate this fact? Okay, and also to not make the model overly complicated. Okay, so that we can do meaningful analysis on the problems. Okay, so what we do is, okay, all these, okay, when we have conditions like this, right, that we are assuming that we know everything, or we know some things very accurately. Okay, like we assume them to be true. Okay, that makes our model deterministic. Okay, that so deterministic basically says that you know pres- precisely about some quantities. Okay, there is no doubt in their values. Okay, so your kinematic and dynamic models that you had made for a robot arm, assuming all the links to be rigid, it was a deterministic model. Okay, so now if you want to incorporate this fact, okay, that yes, all the assumptions might not hold, okay, then what you say, you make a stochastic model. Okay, and basically stochastic model says that you don't know anything precisely, correct? Okay, you know very well how something will behave, but you don't know exactly. Okay, yeah, so this precisely I should not use here. you know for deterministic, you know exactly how some quantities will behave. Okay, but for stochastic, you know very accurately so how some quantities will behave, but you do not know exactly. Okay, you do not know exactly how those quantities will behave, right? So this is where, okay, we bring in probabilities. Okay, because now since we do not know anything exactly, but still we want to be sure of something, okay, that is where we use probabilities, right? That I want my probability that, let us take a example from 2 weeks ago, that the door is open, right? I want the probability to be more than 0.99. Okay, so when my probability is greater than 0.99, that is when I say that yes, I'm really, really sure that the door should be open. Okay, but we are still leaving room for, you know, anything to happen. Okay, basically, there is also a 0.01 probability that the door is closed, right? that the door is closed. Okay, there is a 0.01 probability of the door being closed. So see, you are pretty sure that the door is open. Okay, but you do not know exactly if the door is open or not. Okay, because again, in real world, anything can happen. Okay, it is possible that you are trying to open the door, but like whatever your robot did, it was not successful in opening the robot. Okay, but according to your model, it should have opened. Okay, so this is how we model that corner case possibility that yes, there might be some, you know, situation in which the robot might actually not be able to open the door. Okay, however unlikely that may be. Okay, it does not matter. Okay, but the fact that you can now essentially say that yes, this is also a possibility using a mathematical model is what gives, stochastic methods such an advantage, when your robot goes in real world. Okay, so that is why, we had studied in this week your velocity motion model and your odometry motion model. Okay, so basically what you want to do is you want to predict your states. Okay, and for a 2D case, those states are x, y, and theta, right? Predict states at the new time step given, you know, x, y, and theta at the previous time step and your control input, or basically your input at the current time step. Okay, so you see, you might be, let us say that you know exactly where you started from. Let us, you cannot say that you know exactly where you started from, but let us assume for once that you had known where you started from. Okay, let us assume that you are applying some input. Okay, let us say that this is your, motor. Okay, that you are telling your motor to rotate in a specific way to go from t minus 1 to t. Okay, you, so basically, even if your robot model is really accurate, okay, but you see, let us say I write like this: xt is equal to some function of, or let us take the linear case itself. Okay, it is a t minus 1 plus b u of t. Okay, let us say that, my initial x, okay, this xt a xt minus 1. If I say that this is the case, then let me say that the variance in xt is 0. Okay, because of this. Okay, because I know exactly the a, I know exactly x of t minus 1. Okay, so if I know both of these exactly, and if I say that this relationship is correct, uh, hello Subha. Yeah, hello Subha. Yes, are you there? Okay, well, I'll just continue with what I was explaining in this lecture. Okay, so you can say, okay, like you can assume that you know previously exactly where you were, but you cannot say that you know exactly what will go into the system. Okay, because of course you cannot precisely model anything. Okay, there will always be at some level you will have to do approximations. Okay, so if your model is like this, okay, so basically the stochastic or the uncertainty in the system is coming through your control. Okay, even if you assume, okay, I'm saying again and again, even if you assume that your, you know transition model without the control was really accurate. Okay, but when you apply control, even then, okay, the state it will become stochastic plus b u bar t plus b neta. Okay, and let us call this b neta. Okay, this neta is noise basically in your control. Let us call this as w. Okay, so you see, even even if you were saying that you knew x t minus 1 exactly, still at the time step t, you have a non-zero noise in the system. Okay, so essentially you can only talk in terms of the probabilities. Okay, that what is the probability that I will be at xt given my previous state and my control. Okay, and this probability is given by probabilistic motion models like this. Okay, so this is actually a probabilistic motion model, and it is actually a pretty good probabilistic motion model for linear systems, right? So what you actually do is you predict separately the mean and the variance. Okay, uh, I'll write completely the variance x minus x bar t transpose x t minus x hat t. Okay, let us call this as variance of x of t, right? This is your expectation of x of t, right? So you want this model to be there, okay, for to get estimates of your x at t and your variance of x at t, basically the noise. Okay, and one such model that you have studied in this week is your velocity motion model. Okay, so basically in velocity motion model, you had assumed that you have your x, y, and theta. Okay, this is at t minus 1. Okay, and you want to calculate x prime, y prime, and theta prime. This is at t. Okay, and while going from this to this, okay, because we saw above that there will be some noise that will creep into the system. Okay, so you want an estimate of noise in, again, all three. Okay, so like I think you might have seen this in your lectures also if you have attended the lectures. Okay, that for velocity motion model, what we assume is, okay, we assume that my control is v and omega. Okay, basically the linear velocity and the angular velocity. Okay, and what we assume is that for a 2D robot, for a very small rotation, okay, let us say that this was already at an angle theta. Okay, and if we move it from this x, y, and theta to this x prime, y prime, and theta prime, okay, let us call this delta theta. Okay, and I say that the only input to the system was v and omega. Okay, then what, you know I want to know, given x, y, and theta, and v and omega, what is your x prime, y prime, and theta prime, the new states after you have applied the control. Okay, so like what were we doing in this model? Okay, So what we were essentially doing is we were approximating the center of this circle, of this assumed circle. We have assumed that for very small displacements, for very small delta thetas, okay, the robot is just traversing a circle. Okay, and then we first calculated the center of the circle. Okay, that is like you can calculate it on your own. Basically, you have your x, y, and theta. You have these coordinates. Okay, and then if you know make a line perpendicular to the line joining x y theta and x prime y prime theta prime. Okay, so these two lines, basically I'll draw in red, the intersection of this line and this line. Okay, this will give you, okay, because these will intersect at the center of the circle, right? Okay, so yeah, so I mean there is no point in doing this. You have all done this in your high school while you were preparing for JEE or anything else if you have taken mathematics. Okay, so we'll just write, okay, what is your x prime y prime, and this is just a quantity, intermediate quantity that will come up if you try to find the intersection point. Okay, there is no structure per se that you can just see and understand that why it is coming this way. Okay, this is just math. Okay, you write the equation of this line. Okay, you write the equation of this line. Okay, and then you find the intersection of both, and you will get your center cos theta, then minus x prime sin theta. Okay, so if this is a quantity mu, that is like it is just an intermediate quantity, your x star will come out to be x plus x bar over 2. This is the center point of you know this line connecting our two states, our 2 points, plus mu times y minus y prime. Okay, and similarly for y star will come out to be y plus y prime over 2 plus mu times x prime minus x. Again, there is no structure. Okay, there is a geometric structure to this problem, so that you can just try to see this image and then you want to directly write this. No. Okay, the only geometric structure that you know is that the both these lines, okay, the perpendicular bisector of the line connecting the 2 points and the line going through the center and the initial position, they intersect at the center basically. Okay, so once we have the center of the circle now, okay, so now we can write all these quantities like delta theta, theta, and all. Okay, so let we what we do is we first find the center of this, basically radius of the circle on which we are traveling. Okay, because again I said, right, that for small displacement we can assume that we are traveling on a circle. Okay, so what is the delta theta above, right? This delta theta is this complete angle, that is this complete angle minus theta, right? And what is the complete angle? I told you about the uses of eta and 2 in one of the previous sessions. Okay, basically it preserves the quadrant information, okay, in which you have. So basically this is the angle that this x prime y prime makes from the center of the circle, and minus your basically theta. Okay, that is your x minus no y minus y prime and x minus x prime. Okay, so now you have your delta theta. Now what should be the velocity? Okay, your velocity uh, or like per se, your estimated velocity, okay, the control that you should give, the velocity that you want to give for it to reach, your desired states is what? Okay, r star delta theta. Okay, this is the linear displacement. And we're saying that is happening in time delta t. So this is basically delta theta over delta t r star. Okay, and your omega is again now, since we are changing by this much angle, in delta t time. So this is my omega. And now I'm not sure that if my theta plus delta theta, if it is exactly theta prime. Okay, I'm not sure, right? So what I do is I define another quantity, I call it as gamma hat. And what I do is I give the desired omega, okay, because I want the actual omega to be this, right? Theta prime minus theta, because I want to reach theta prime. And I subtract omega. So basically, this quantity will, it will go to zero as your theta plus delta theta. It actually goes to theta prime. Okay. So now what is the noise, final noise? Okay. The final noise is probability of, okay, okay, like you have defined in the lectures also, it is defined a comma b, where a is the, okay, this is a distribution with zero mean, and b is the variance. Okay, so in our case, the noise will be probability of the actual velocity that I'm giving minus the estimate of the velocity, okay, from the model here. Okay, that how much velocity, you know is required for it to move. Okay, and then, so what we do is we take the variance as a, okay, we tailor this variance, as a, as like this, like alpha 1 times magnitude of v plus alpha 2 times magnitude of omega. So essentially the idea here is that alpha 1 is chosen such, based on the effect of the magnitude of v on, the whole, this mean, okay, or basically the whole estimate. Okay, essentially whatever quantities we have, we multiply them, because we are assuming that everything is independent, right? Okay, so we want our omega and omega hat also to be the same. That's why this whole quantity becomes zero mean. Okay, and again, we choose alpha 2 and alpha 3 based on their effect on this omega minus omega hat. And the third quantity also, it is multiplied with these two. It is your gamma hat, only gamma hat, because we said, right, that we want our gamma hat itself to go to zero. And then again, you know, we take the variance, we tailor the variance like this. Okay, this is just how we're doing this. Okay, this is our assumed variance. And like these probability distributions, you can go and see in the lectures also. You can either take Gaussian normal with zero mean, okay, or you can take, your triangular distribution. Okay, basically your Gaussian normal goes like this. Okay, that at zero mean, because we want the mean to be zero. Okay, so it comes like this. Okay, it is shaped like a bell about zero. Okay, this is your Gaussian with 0 sorry. And okay, you can also make it triangular. Okay, so basically the probability here, you can see that the probability is non-zero everywhere. Okay, it is very small, but it is never zero. This is a probability. Okay, and for triangular distribution, the probability is actually zero. Okay, when you know it is out of these bounds. Okay, so this is your Gaussian and this is your triangular probability distribution. You can use more distributions. Okay, that is up to you. Okay, you might have seen in the rangefinder example, okay, that you have used four different probability distributions. Okay, and every probability distribution has a reason. Okay, has a particular characteristic that you wanted your, you know, model to have. So I think you guys have done pretty much, you know, if you have seen the lectures, you might pretty much know all this already. Okay, so since also like there is no student currently in the meet, so I think I'll just stop here. And if you guys are seeing this as a recorded lecture, as you might have seen earlier also, then you can just, if you have any doubts, you can just comment on this, and I will try my best to resolve, your doubts that you have from the comments itself. So thank you for attending. Like one guy had attended here, he's already left. So yeah, I'll just stop the video. Thank you.